Hi everyone. So I just wanted to make a video on blocking IO and non-blocking IO, and single-threaded IO and multi-threaded IO. Okay. So since the day we have been working with Node.js or Fast API, we have been working with single-threaded and non-blocking IO. So we hear this non-blocking IO so much that we don't even know what's actually the problem of a blocking IO and what's the problem of multi-threading with blocking IO. All right. So let's see first how a blocking IO actually looks like. All right. So here I have a single threaded server. Okay, I have a single threaded server. A socket. Um, a server is basically a listening socket, and when we accept from that listening socket, we basically accept a queue from the connection queue, and we get a connection socket. So the socket by default, the socket is blocking. All right. So in this case, in this code, we have a blocking IO. So let's just simply port this code into my Raspberry Pi. Um, and now let's simply run the container. Okay, so let's go ahead and see it the store single threaded. Um, Sorry, not this one. I'm gonna execute the Docker stats data store single threaded. Here's my Docker stats, and I can see the CPU usage is around 0% because it's not a CPU bound task, right? This is an IO bound task. Because the difference between CO bound task and IO bound, CPU bound task and IO bound task is that in CPU bound task, you will get the CPU. You will not wait for something to be completed. But in IO bound task, you are waiting for the IO operation to be completed. That means you are IO blocked. All right. That means we are IO blocked and we are not seeing any CPU usage at the moment. Even if I Okay, first of all, let's see that we're actually blocked. All right, 268.0.8. The port is 8000. Okay, so we're trying to connect with one client. We're connected. Now let's see. Let's try to connect with another client. All right, we're not getting connected. Right, we're here. We're connected, but here we're not. Here we're not connected. We're blocked. Okay. Now let's unblock this. Let's just make a very simple query. We can see now we're unblocked. So the second connection is actually blocked by the operations of the first connection, because the first connection we're reading from the first connection and we're blocked. So every time we receive something in the first connection, we get unblocked, and then the other connections get the reading from the socket. All right. So this is what a blocking IO actually looks like. And let's do some load testing. All right. Let's do some load testing. I'm gonna have around like 100 of virtual users. What's the logs? What are the logs, by the way? Okay, we're doing some load testing, but for some reason we're not seeing the CPU usage. But anyways, here we can see we're still not doing any sort of CPU usage, right? Oh, why it's not working? By the way, USB server, C server. Yeah, okay, so the thing is like we are actually connecting, we're trying to connect, we're sending the commands, but as I said, we're blocked. So as we're blocked, we're not actually seeing any output here because we're not receiving any response, right? We're blocked. And we can see the CPU usage as well, it's around 0%. It makes sense because it's an IO bound task and we're blocked. Now let's see what happens in the case of multi-threaded server. All right, so stats store threaded. So the multi-threaded as well, we're seeing the CPU usage is around like 0%. Now let's do this load testing on multi-threaded server. Okay, we get 100 of virtual users. Right now we're actually getting response because we're not blocked. Okay, why we're not blocked? Because we are basically handling each connection socket with a thread. Each thread is actually handling each connection socket. Okay, here we are dedicating one particular thread to one particular connection socket. That means even if the socket the IO is blocked, but since the thread by itself is non-blocking, so even if the IO is blocked, another IO is being handled by another thread. Okay, um, so this is this is non-blocking because the threads are non-blocking and each thread is actually handling one connection socket, but the connection sockets themselves are blocked. So if we look into the CPU usage, it's around 12.70%, or like around 8 to 12%. It's not 3% or 8% whatsoever. But there's a problem. Okay, before going into the problem of the multi-threaded server, um, let's see something. Let's make the single threaded server from blocking to non-blocking. When it will be non-blocking, then we can handle multiple connections concurrently, right? No connection or no connection packet or no connection message will be blocked for any other connections. Okay, so let's go ahead and try this out. Let me stop the slow testing. By the way, we are probably still doing load testing on this. We're not. Okay. So now the single-threaded IO server is not blocked. Okay, we have removed the block, and now let's see what happens. Okay, so let's again try to connect. We're connected. Now let's go through the another client. Again, we're connected here. We're not blocked. Okay, let's try to send some commands from here. The command was handled. Again, the command was handled. Nothing is blocking anything else. Okay. Now let's take a look at the CPU usage of the single-threaded non-blocking IO server. You see, now we're having much more CPU usage. All right. If we do some load testing in this case, all right, let's see what happens when we load test. You can see previously it was around 10% of CPU usage in the multi-threaded blocking IO server, but now when we're doing a single-threaded non-blocking IO server, we're having a CPU usage of around twice the multi-threaded uh, blocking IO CPU usage, right? Because since the IO is now non-blocking, I'm looping over the connection sockets and the listening socket more and more, and which is making a lot of kernel level system calls, and that's the reason why we're getting the CPU usage. Now, primarily, we may think, okay, we are doing so much CPU usage in single-threaded non-blocking IO. Well, single-threaded when the IO is non-blocking, it's actually a CPU bound task. So it's not an IO bound task, to be honest. So primarily, we may think, okay, single-threaded servers or single-threaded non-blocking IO is actually doing more CPU usage than the multi-threaded blocking IO. Then why would we even care to use a single-threaded non-blocking IO? Rather, we could have used multi-threaded IO very easily, right? Okay, because when we're dealing with multi-threading, it's quite simple. You get a socket, you get a connection socket, and you dedicate a thread to that connection socket to read from that connection socket. Even if the connection socket is blocked, the operating system is taking care of all the scheduling of the threads. You don't need to do any sort of hassle. You don't need to write the logic of controlling those connection sockets in a loop, right? So when you're dealing with multi-threading, things become a lot easier. So why would we even take the approach for single-threaded non-blocking I/O, but the single-threaded non-blocking I/O is making more CPU usage than multi-threaded blocking I/O? All right. What we have done in a single-threaded non-blocking I/O is that we are receiving a connection, we're storing the connection, and then we're looping or iterating through those connections and reading a chunk of bytes from those connections. If the connection is blocked, then we're receiving an and blocking IO error, and then we are passing to the next connection. So we're not blocking. All right. But still, we have to write this loop of handling all those connections. We have to take the hassle of storing those connections upon receiving those connections from the listening socket. We have to make the workaround to make this whole thing workable, right? We have to write our own loop for iterating through those connection sockets. But in the case of multi-thread, we didn't need to do anything. We just simply receive a connection socket from the listening socket. We assign a thread to that connection socket, and that thread was basically listening from that connection socket in the loop. Even if those connection socket was blocking, but by the nature of multi-thread, threads themselves are non-blocking. So the CPU schedules one thread over another when one thread is blocked, right? So why would we even care to use a single-threaded non-blocking I/O where a single-threaded non-blocking I/O is making more CPU usage than a multi-threaded blocking I/O, right? The question is, and the answer is very simple. When we're dealing with multi-threaded, whenever we're dealing with multi-thread and we are assigning each connection to one particular thread, then we may end up with a huge amount of thread in a very peak moment. Yes, but modern hardwares, modern operating system, modern runtimes, they actually do a lot of optimizations. They definitely don't loop through all the connections. They use efficient system calls like epoll, but this is a very naive application, a very naive implementation to understand the essence of blocking or non-blocking I/O. But the point is, when you are dedicating one particular thread for handling each connections and you're spinning up one thread on each connection, you may end up in a huge amount of threads on a peak connection, because when you have around 1 million HTTP requests in a second, HTTP requests themselves behind the scene are TCP connections. So if you have 1 million requests in a second, you may end up with 1 million threads, because each of those threads are actually handling each of the connection. All right. So this is where the memory usage becomes really dirty. All right. Let me show you the memory usage of a multi-threaded server under heavy load. So I don't know why Docker stats doesn't actually show me the real memory usage. Maybe because of some abstraction that Docker does behind the scene. But we can actually go into the machines or the usage of the machine itself. Store htop. Okay, so we have this htop visual here from the multi-threaded TCP server, multi-threaded non-blocking TCP. So here we can see now there's only one thread. There's not more than one thread, You can see there's these two processes are running right now. One is or these two tasks are running right now. One is this command and another one is this htop. Currently this Python server is or this process is in sleep state, and the htop is at running state. So now let's do some load testing. Okay, in this multi-threaded server in this multi-threaded server, let's make a very let's make it just around a 10 peak user peak concurrency load. Okay, so now if we look here, we can see we can see threads, right? Threads are spinning up. How many threads? One, two, three, four, five, six, 7, 8, 9, 10. 10 threads have spinned up for 10 users, 10 connections, right? Okay, so we are ending up with threads. We are using memory. Every time you spin up a thread, you need to allocate at least 4 kilobytes of memory into that thread, and that's the reason why Golang had brought up concepts like coroutine, which is more memory efficient, lightweight threads. So whenever you spin up a kernel thread, you have to make a system call to the kernel. For you have to switch to the kernel mode from the user mode. You have to make a system call to spin up a thread, and when the thread is spinned up, you have to allocate at least probably 4 kilobytes of memory, or maybe more or less. I'm not sure, but you have to spin up threads, and you have to allocate memory for that thread. All right, and this memory that you're allocating for the thread is actually shared in your process. So now let's see what happens. Currently, we're using around 702 megabytes of memory. We have around 8 gigabytes of memory. What happens when we increase the load? All right, let's say we are stopping the load. We'll stop the load. Let's say our load is around 10,000. What happens? Just take a look at the memory usage. We are using around 1.1 gigabyte of memory. 1.1 gigabytes of memory, or 1.15, 1.17. It's just increasing. Like 1 point, like more than 1 GB of memory you're using. It's actually very huge. It's really hard to break any uh, general purpose servers, right? Because when you're taking a server, having an 8 GB of server or like 4 GB of server is quite expensive. When you do when you spin up so much threads, maybe the shared host CPUs you get for deploying your cPanel applications, probably they have around 512 megabytes of memory, and you are using around 1.6 gigabytes of memory, which is really huge, right? So now let's see, under the same load, how the single threaded server behaves. Okay. um, by the way, what was the memory usage with CPU usage? um, okay, CPU was probably around, yeah, 0.57 whatsoever. Okay, so now let's see the memory usage and the CPU usage for the single threaded server under the same load, the single threaded non blocking server. We previously seen that single threaded non blocking server is more CPU intensive, it's more CPU bound, it uses more of the CPU than the multi threaded blocking IO server. Now let's take a look at the memory usage of the single-threaded, non-blocking, CPU-bound server. Okay, store stop. Okay, so it's running in probably 8089. Let's stop this first. New load. Okay, 10,000 counts. Let's load it. Okay, so what we're getting here is around 890 of memory, but this memory is actually the core memory of the Raspberry Pi, the machine I'm using. So there is also an overhead of the another containers that's running in that machine. Let me just wipe that out. Docker, stop that out. Stop. Data store. Now let's see. Um, CID data store single threaded H top. Um, yeah, we're having a bit improvement in the memory usage since we have stopped one container. Now let's run the load test. 10,000 of peak concurrency. Okay, in this even in this load, we can see our memory usage is somewhat around 800 megabytes, but previously it was like like more than 1.5 gigabytes. So memory usage is actually very crucial, a very crucial, what should I say, a very crucial um, metric because like servers crash. You see servers crash on a very high peak load. One of the reasons why they crash is because they get out of memory. So when you are using less memory, it gives you more chances of your server to be more available and less crashing. All right. So the memory usage is a very, very important thing. It's a very crucial metric of your server. So we can see that even if we're having way more CPU usage in this case, but the memory usage is very low. All right. Although in this case we have run a single process, and we haven't actually like utilized the multiple cores of the CPU. All right. In order to do that, we can do something which is clustering. All right. We can spin up multiple processes, and then those processes will be scheduled into the multiple cores, and we can actually take advantage of the parallelism of the CPU cores. All right. So in here, I have another server which is a single threaded cluster where I have basically forked. I have forked processes, and in each process, I am running this non-blocking single-threaded I/O. All right. So let's see how many containers we're running now. We are Yes, we have this cluster here. So Docker exec it data store single threaded cluster htop. Okay, here we are. Now let's do the same load testing on this cluster. All right. So you see now we are having the CPU usage here as well. But the thing is, in this case, no one particular core is actually getting all those loads, and other cores are waiting. All right. All the cores are equally distributing the load, and all the cores are equally working together because we have spawned multiple processes to each of the cores, and each of the processes are having a single thread, and those threads are handling this non-blocking IO. All right, and you can see here as well we have four processes. We have four processes which are currently at running state. All right. I mean, they are being scheduled by the CPU, the OS, and some of them are in ready state, some of them are in sleep state, some of them are in uh, running state. The thing is, we are utilizing the CPU more. So this actually gives us a very important insight that if you are out of resource and you want to scale your application, you don't need to always scale your application horizontally, because when you scale your applications horizontally, horizontal scaling comes up with complexities like routing, sticky load balancing, unsticky load balancing, stateless load balancing, um, maybe a partition miss, like complications gets added up. If you can actually vertically scale your application, and you are actually utilizing the vertical scaling of your application. Like let's say you are running a server in a 2-core CPU, but now you have vertically scaled your server, I mean your application, and you're running your server right now at an 8-core CPU, but you're not actually utilizing all those CPUs, right? If you have a very predicted amount of traffic, like it's not spiking up and down, it's statically at a very high load, you really don't need to come up with horizontal scaling, because you know you have high load. So why would you not take a more powerful server like 8 core or 4 core? But regardless of how many cores or how much vertical scale you're doing, if you are not utilizing all the CPU cores or all the CPU, then it's pointless to vertically scale your application. All right. So this is a very important insight, that even if we are vertically scaling our application, we are assigning more powerful server, more powerful CPU, we have to make sure that our application is actually using that extra CPU or that extra power of the CPU. All right. So the core insight is, we know about CPU bound task and IO bound task, but when the IO is non blocking, then it's not an IO bound task. It's actually a CPU bound task. All right.